Hello students, in Easy Physics Learning, we'll go with Higher Secondary Physics, first unit Electrostatics, electric dipole in electric field. So look at this diagram. We have drawn equispaced parallel lines shown in red color that indicate uniform electric field. What does mean by uniform electric field? If the field at every point is the same, both in magnitude as well as in direction, then we say the field is uniform field. So look here, we have an electric dipole minus q and plus q separated by a distance 2a. We say this arrangement is electric dipole. This electric dipole is now placed in the uniform electric field so that the dipole axis is making an angle theta with the electric field. You know, friends, when a charge is placed in the electric field, it experiences force. And that force formula is F is equal to Q into E. If the charge is a positive charge, you remember, the force will be in the direction of electric field. If it is a negative charge, then the force will be opposite to the direction of electric field. Now, in this arrangement, both the charges, magnitude-wise, they are equal, placed in the same electric field. So, the forces will also be equal, but only difference is the directions are opposite. Why the directions are opposite? Because one is positive charge, other one is negative charge. The sign differs, so the direction also differs. Okay. Now, at the two ends of the dipole, there are two equal forces are acting. And these two equal forces are directed opposite but not acting in the same line. They are acting at different lines. So now, these two forces will cancel each other. So net force will be 0. But since the line of action are different, it will make the dipole to rotate. Yes, the upper end will be forced towards right, lower end forced towards left. So you have two forces which will make it to move in the clockwise direction. So this dipole will experience a rotation. What is the name of the force that is responsible for rotation? It's torque. So the dipole will experience a torque. How long this torque will act? Till the dipole gets aligned to the field. If it gets aligned to the field, after to that, the two forces will act in the same line, so they'll cancel each other. Till then, there will be a torque acting on the dipole. Now let us see how to find this expression for torque. So what's the general formula for torque or moment of force? Is the product of distance from the point of rotation or axis of rotation and the force. It's a cross product. Usually we write it in notation R cross F. So here, if you consider the force acting over the minus q charge, then the distance from the axis of rotation is OA vector. And this force is minus QE vector. Now this cross product is OA vector cross minus QE vector. The same like if you go for the positive charge, there the distance is OB vector and the force is QE vector. So that is the next torque. If you want the overall torque, it's OA vector cross minus QE vector plus OB vector cross QE vector. Okay. Now, you know friends, OA vector is equal to minus AO vector. So instead of OA vector, we'll put here minus AO vector and followed by the second term as it is. Now you see here, here's minus, here's another minus, minus into minus will become plus. So the next step, we take it as AO vector cross QE vector and then OB vector cross QE vector. Now in both the terms, QE vector are there, can be taken as common. Within bracket you can write AO vector plus OB vector. What is AO vector plus OB vector? That is AB vector. See, we have taken QE vector as common. The next step, AO vector plus OB vector can be written as AB vector. So you are getting the expression for torque as AB vector cross QE vector. What is A cross B? It's AB sine theta n cap. The same like here, it's AB vector cross QE vector. AB, the full length is nothing but 2A. So instead of AB, we have written here 2A. 2A, then QE sine theta n cap. What does that n cap represents? It's the direction of the resultant torque. How do you find the direction of a cross product? When you cross two vectors, the resultant can be known by Maxwell's right-hand corkscrew rule. How to find the direction? You rotate the screw from the first vector to the second vector. What's the first vector here? It's the AB vector. So this is the first vector. Second vector is a field vector. Now we are going to rotate the screw from AB vector to the field vector. How will you rotate the screw? You have to rotate like this. That is clockwise. Now friends, you place the screw such a way the tip is pointing over the plane of the paper and rotate the screw clockwise. Which direction the screw will move? Yes, the screw will get into the paper. That's the direction of torque. So now for this case, the torque is directed into the paper. That is shown here. You see, the torque is into the paper. But how do you know the direction of torque? You can know it by using Maxwell's right-hand corkscrew rule. Make it clear, okay? Fine. Now, if we consider the magnitude alone, we go back to the previous step. See here, I have explained you how you are getting the torque expression. But once again from the previous expression, I go for mere magnitude of the torque. Then I don't have to go with all these steps. Magnitude of torque is OA magnitude, QE magnitude, A cross B is AB sine theta. So there is sine theta here. The same like for the second term, there is sine theta. OA is small a, OB is also small a. So you get small a QE sine theta, again small a QE sine theta. Together you can write 2a QE sine theta. So QE 2a sine theta. That's written here. Same steps. You're getting 2a QE sine theta. But you know already electric dipole moment is 2aq. So instead of 2a and q in this expression, we substitute p vector. So now you get torque is p e sine theta. Here only magnitude is shown. If you want to be shown with the direction, you can put n cap. So finally we have got expression for the torque experienced by an electric dipole placed in the uniform electric field. This expression can also be shown by a cross product. So tau vector is p vector cross e vector. Now from this expression you can find the direction also. Good. Now which will affect the magnitude of this torque? So the value of torque depends on dipole moment, electric field as well as the angle. If dipole and field are the same, then based on the angle, the torque value will differ. How long the torque will act? The torque will act as long as the dipole tends parallel to the field. Suppose if the dipole becomes parallel to the field, then the value of theta will be 0. Naturally sine 0 is 0. Torque will become 0. That's what I explained here. The torque tends to rotate the dipole and align it with the electric field. Once P is aligned with the field, then the total torque on the dipole becomes 0. Now for different angles, let us see what will happen to the value of torque. If theta is 0, either theta is 0 or theta is 180 degree, naturally the torque will become 0 because sin theta will become 0. Sin 0 is 0, sin 180 is also 0. Theta 0 indicates the dipole is aligned parallel to the field. Then sin 0 is 0, naturally the torque will become 0. The same like if theta is 180 degree, dipole is anti-parallel to the field, then again sin 180 is 0, naturally the torque is 0. Suppose if theta is 90 degree, then the dipole is perpendicular to the field. What is sin 90? Yeah, it's maximum, 1. Then automatically the torque becomes the maximum. Okay, for various different angles we'll have different value of torque. So here we have discussed with the torque acting on the dipole placed in the uniform electric field. Only torque acts in the system. What happens to the net force? If the field is a uniform field, then the net force will become 0. Why the net force becomes 0? It's because the force in two opposite directions are equal, so they cancel each other's effect. The dipole will experience only rotation and no net force. So have it clearly in your mind. If a dipole is placed in uniform electric field, whatever may be the angle, the net force will become 0. The angle decides only the value of torque and not the net force. Good. Now let us see what happens when the dipole is placed in non-uniform electric field. Look at this diagram. The field lines are not parallel and their density is getting varied. That means the field is non-uniform field. The value of field is different at different points. Now we have a dipole placed in this non-uniform electric field. Now what happens? Like what we discussed already, over this plus q charge, there is a force q E1 vector, which is directed along the direction of field. Over the charge minus q, there is another force which is directed opposite to the electric field. Now, both the forces are opposite but not equal. Why? Because the field values differ. See, E1 is not equal to E2. So both the forces are not equal, but they are directed opposite. So naturally, the forces cannot cancel each other, so there will be a net force. Remember, if a dipole is placed in the non-uniform electric field, then there is a net force. Which direction the net force will be? At which point the field is more towards that direction. Suppose field is more in the place of minus q, then it will be directed opposite to the field. If the field is more in magnitude at the point of plus q, then the resultant force will be in the direction of the electric field. Okay. Then for torque, the usual formula what we followed already. So see here, if the dipole is placed in the non-uniform electric field, then force acting on plus q will be different from the force acting on minus q. So there is a net force. Both the forces will not cancel. Thus there will be a net force acting on the dipole. So remember the discussions which we have made now. If you want to know the net force acting on the system or not, you have to look at the field. If you want to find the torque, you have to think over the angle. Good. Now let us see to a simple problem. Look at this problem. A sample of HCl gas. HCl is a dipole. So a dipole gas is placed in the uniform electric field. Field magnitude is given. Dipole moment is also given. You are asked to find the torque. Very simple and very easy problem. What's the formula for torque? Yeah, It's P E sine theta. So look here, dipole moment P is given, electric field is also given. What about the angle? That's given in the question. You want to get the maximum torque. When you will get maximum torque? When theta is 90 degree, that is dipole is perpendicular to the field. Let us go ahead. Field value is 3 into 10 power 4 Newton per Coulomb. Dipole moment is 3.4 into 10 power minus 30 Coulomb meter. Given in the data. Yes. Now, for maximum torque, theta has to be 90, sine 90 is 1. Now we go ahead with the formula. Tau is equal to Pe sine theta and maximum torque theta is 90. So it's mere P into E. We multiply both the values. You get the answer. The maximum torque is 10.2 into 10 power minus 26 Newton meter. Fine. We have discussed about a dipole placed in uniform and non-uniform electric field.